There are moments in science when an instrument built to refine an existing framework instead exposes its limitations. The James Webb Space Telescope was engineered to extend the reach of observational cosmology, probing the high-redshift universe with unprecedented infrared sensitivity and angular resolution. Its primary objective was not to overturn the Lambda Cold Dark Matter model, but to constrain it with precision data from the epoch of early galaxy formation. However, the first deep-field observations released in July 2022 revealed systems at redshifts greater than 10 that appeared unexpectedly massive, luminous, morphologically evolved, and in some cases chemically enriched. Such characteristics challenge conventional timelines for structure formation, stellar population synthesis, and early feedback processes. Rather than simply confirming existing simulations, Webb's data have introduced measurable tension within standard cosmological assumptions. What was expected to be a validation exercise has instead become a catalyst for theoretical reassessment. The observable universe has an edge, and we can almost see it. The universe does not have an edge in the way that a room has walls. There is no boundary you could reach, no wall you could press your hand against, no sign marking the end of space and the beginning of whatever might lie beyond it. The universe, as far as physics can determine, extends in all directions without a physical limit. What has an edge is not the universe itself, but our access to it. There is a horizon beyond which no information has had time to reach us, a boundary defined not by space, but by time and the finite speed of light. This is the observable universe, and understanding it is the essential starting point for understanding what Webb found when it looked as close to that boundary as any instrument ever has. The observable universe is a sphere centered on Earth, not because Earth occupies any special or central position in the cosmos, but because we are the observers. Light travels at a fixed speed of approximately 186,000 miles per second. The universe has a finite age of approximately 13.8 billion years. These two facts together create a horizon. Any object more than 13.8 billion light-years away in light travel distance cannot have sent us a signal that has had time to arrive yet. Its light is still traveling toward us. We cannot see it. We cannot know it exists. It is outside our observable universe, not because space ends there, but because time has not permitted its light to reach us. The actual radius of the observable universe is larger than 13.8 billion light-years, and this requires explanation. Space itself has been expanding since the Big Bang. A photon emitted from a distant object 13.8 billion years ago was not traveling across static space. It was traveling through space that was simultaneously expanding beneath it, stretching the photon's path. By the time that ancient light arrives at our detectors, the object that emitted it has been carried much further away by the expansion of space. Accounting for this expansion, the edge of the observable universe sits approximately 46 billion light-years away in what cosmologists call co-moving distance. The observable universe is a sphere roughly 93 billion light-years in diameter. Within that sphere sit an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions to trillions of stars. Each star is a nuclear furnace, and many host planetary systems. The scale of what the observable universe contains is genuinely beyond the reach of human intuition, but the edge of it, the cosmic horizon, is where things become scientifically extraordinary. The light arriving from objects near that horizon is ancient. It left its source when the universe was only a few 100 million years old. It carries information about conditions that existed when the cosmos was a fraction of its current age, when the first structures were just beginning to condense out of the hot, nearly uniform plasma that filled everything after the Big Bang. Before Webb, the farthest objects ever observed in detail were galaxies seen as they existed roughly 400 to 500 million years after the Big Bang. The Hubble Space Telescope, in its deepest exposures, the Hubble Deep Field, the Hubble Ultra Deep Field, the Extreme Deep Field, had pushed that boundary with extraordinary effort, staring at single patches of sky for hundreds of hours to collect enough ancient photons to build usable images. What Hubble found at the edge of its reach were small, irregular, faint smudges of light, the earliest galaxies it could detect, primitive and indistinct, fitting neatly into the models that cosmologists had developed to describe the early universe. Webb was designed to push beyond Hubble's horizon. Its larger mirror, its infrared sensitivity, and its position far from Earth's atmospheric interference allowed it to detect light from objects that Hubble could never resolve. Webb can observe galaxies as they existed 200 to 300 million years after the Big Bang, within the first 2% of the universe's current age. It can detect individual bright stars in some of the closest early galaxies. It can measure the chemical compositions of gas clouds in the early universe. It can, in principle, observe objects closer to the cosmic horizon than any instrument before it. The infrared capability is critical and worth dwelling on. The universe's expansion does not merely carry distant objects away from us. It stretches the light those objects emit. A photon emitted as visible light by a galaxy 13 billion light-years away arrives at Earth shifted dramatically toward longer, redder wavelengths. By the time the most ancient observable light reaches us, it has been stretched from visible or ultraviolet wavelengths all the way into the infrared. Hubble's instruments, optimized for visible and ultraviolet light, simply cannot see this redshifted ancient radiation. Webb's instruments, designed specifically for infrared wavelengths, can. This is why Webb sees what Hubble cannot. It is not merely a bigger telescope, it is a telescope tuned to the frequency of the oldest light in the observable universe. When astronomers trained Webb on empty patches of sky and accumulated exposure after exposure, they were essentially looking backward through time toward the cosmic horizon. Every photon captured from a distant galaxy is a message from the early universe, delayed by billions of years of travel through expanding space. The telescope is simultaneously a space telescope and a time machine, and the era it can access, the first few 100 million years after the Big Bang, is the era when the universe was building its first structures from scratch. Understanding this temporal depth is essential for grasping why Webb's findings were so surprising. The objects at the edge of Webb's vision are not merely far away, they are young. They existed when the universe had barely begun. And what they look like, how massive they are, how structured they are, how chemically complex they are. All of this should reflect the primitive conditions of a cosmos that had only recently emerged from the hot uniform state of the Big Bang. The standard model of cosmology made specific quantitative predictions about what those conditions would produce. Webb looked, and the early universe did not match the predictions. Redshift is the universe's most honest measurement tool. Before examining what Webb found, it is necessary to understand how astronomers know how far away anything is. Distance measurement in cosmology is not straightforward. You cannot send a ruler to a galaxy 13 billion light-years away. You cannot bounce a signal off it and time the echo. The universe is too large and the objects too remote for any direct distance measurement technique. What astronomers use instead is redshift, and understanding it is essential because every Webb discovery about the early universe depends on measuring it with precision. Redshift is the cosmological version of the Doppler effect. When a source of waves moves away from an observer, the waves it emits are stretched. Sound waves from a receding car have a lower pitch than sound waves from an approaching one. Light waves from a receding galaxy are shifted toward longer, redder wavelengths. They are redshifted. The greater the recession velocity, the greater the redshift. In an expanding universe where every galaxy is moving away from every other galaxy, the degree of redshift tells you how fast an object is receding. And because the universe's expansion follows known physical laws, recession velocity tells you distance. Astronomers measure redshift through spectroscopy, splitting a galaxy's light into its component wavelengths and looking for the characteristic fingerprints of known elements. Hydrogen, for instance, absorbs and emits light at specific, precisely known wavelengths. In a nearby galaxy, these hydrogen absorption lines appear at their laboratory wavelengths. In a distant galaxy, the same lines appear shifted toward the red end of the spectrum by an amount that reflects how much the universe has expanded since the light was emitted. The ratio of the observed wavelength to the emitted wavelength defines the redshift, denoted by the letter Z. A galaxy with redshift Z equals one has had its light wavelength doubled during transit, meaning the universe has expanded to twice the size it was when the light was emitted. A galaxy with equals 7 means the universe was 1/8 its current size when the light left. The relationship between redshift and time depends on the expansion history of the universe. But for high redshift objects, the correspondence is roughly this. Redshift Z equals 6 corresponds to a universe about 900 million years old. Redshift Z equals 10 corresponds to about 450 million years. Redshift Z equals 13, the current frontier of Webb observations, corresponds to a universe only about 300 million years old, roughly 2% of its current age. Before Webb, the highest confirmed spectroscopic redshift for a galaxy was approximately Z equals 11, corresponding to the galaxy GN-11 discovered in Hubble data and confirmed by subsequent ground-based observations. This galaxy existed about 400 million years after the Big Bang and was already surprisingly bright and massive for its age. A puzzle, but one that could be accommodated within existing models with some theoretical flexibility. Webb was expected to find more such objects, perhaps extending the confirmed redshift record modestly and filling in the population statistics of early galaxies. What Webb actually found were galaxies with spectroscopic redshift of Z equals 12, 13, and beyond. In its first year of science operations, Webb identified and confirmed objects existing as early as 320 million years after the Big Bang. Some photometric candidates, objects with redshifts estimated from the shape of their light profiles rather than confirmed spectroscopically. Suggested redshifts as high as Z equals 16 or 17, corresponding to a universe perhaps 230 million years old. These candidates await spectroscopic confirmation, but several have held up under scrutiny from multiple analysis teams. The distances these redshifts imply are staggering. Light from a galaxy at Z equals 13 has been travelling for approximately 13.5 billion years. The galaxy that emitted it has, through the expansion of space, been carried to a current distance of roughly 33 billion light-years. But what makes these measurements scientifically explosive is not the distances themselves. It is what those distances imply about the ages of the galaxies and what those ages imply about the physics that produced them. At Z equals 13, the universe was only 300 million years old. 300 million years sounds like a long time by any human standard. In cosmological terms, it is barely the opening chapter of a story that spans nearly 14 billion years. The standard model of cosmology, the Lambda Cold Dark Matter model, or Lambda Cold Dark Matter, makes explicit predictions about what galaxies should look like at these redshifts. The model describes how dark matter clumps under gravity in the early universe, forming halos that attract ordinary matter. Gas falls into these halos, cools, and begins forming stars. The first galaxies are predicted to be small, with relatively low masses, modest star formation rates, and simple chemical compositions reflecting the fact that almost no heavy elements had yet been produced. Building large, massive, chemically complex galaxies take a time for many generations of stars to live and die, seeding the gas with the heavier elements that stars forge in their nuclear interiors. The predictions are specific enough to be tested. At Z equals 10 and beyond, the Lambda Cold Dark Matter model predicts a particular abundance of galaxies of particular masses. It predicts that the most massive early galaxies should contain no more than a few billion solar masses in stars. It predicts that these galaxies should be irregular and unsettled, still in the chaotic early phases of assembly. It predicts a particular rate of star formation consistent with the limited time available and the relatively modest concentrations of gas. Webb measured these properties directly for the first time with sufficient resolution and sensitivity to be conclusive. The results did not match the predictions, not marginally, not within the error bars of a challenging measurement. They missed by amounts that cosmologists described, in the careful language of published papers, as statistically significant tensions, and in the less careful language of conference hallways as genuinely alarming. The first galaxies were not supposed to look like this. The standard picture of how the first galaxies formed is built on decades of theoretical work, computational simulation, and indirect observational evidence. It describes a process called hierarchical structure formation, in which small things build first and large things assemble later. After the Big Bang, the universe was extremely hot and nearly uniform. As it cooled, dark matter, the invisible gravitational scaffolding that makes up about 27% of the universe's total energy content, began to clump under its own gravity. Regions that were very slightly denser than average attracted more dark matter from their surroundings, while slightly less dense regions were depleted. Over hundreds of millions of years, these dark matter concentrations, called halos, grew through mergers with each other, progressively building larger and larger structures. Ordinary matter, gas, initially almost entirely hydrogen and helium, followed the dark matter gravitationally. Gas fell into dark matter halos, heated up as it compressed, then slowly radiated away its energy and cooled, sinking toward the center of the halo where it could form stars. The first stars ignited in the densest dark matter halos at redshift somewhere between Z equals 20 and ZS equals 30. According to simulations, perhaps 100 to 200 million years after the Big Bang. These first stars, called population 3 stars, were made of essentially pure hydrogen and helium. They were expected to be extremely massive, living fast and dying violently as supernovae, seeding their surroundings with the first heavy elements and triggering the formation of the first recognizable galaxies. The first galaxies in this picture were small. The dark matter halos available in the first few 100 million years had not yet had time to grow large. The halos contained relatively modest amounts of mass, and the galaxies that formed within them reflected this modesty. They were irregular assemblages of a few million to perhaps a few 100 million solar masses in stars, objects that would appear as faint, tiny, disturbed smudges if we could observe them. The process of building a galaxy like the Milky Way, which contains hundreds of billions of stars, would take billions of years of hierarchical merging and gas accretion, not hundreds of millions. This picture made specific, testable predictions. At Z equals 10, the number density of galaxies more massive than 10 billion solar masses should be essentially zero. No such objects should exist that early in cosmic history because the dark matter halos capable of hosting them had not yet assembled. At Z equals 8, some moderately massive galaxies should begin to appear, but they should be relatively rare, and their properties should reflect the early metal-poor universe in which they formed. Webb's first deep field images, released to the public in July 2022, immediately showed something was off. The images revealed candidate high-redshift galaxies that appeared, even in initial analysis, to be too numerous and too bright. Early photometric estimates of these galaxies' properties suggested masses exceeding 10 billion solar masses at redshifts of Z equals 10 and beyond. Follow-up spectroscopic observations confirmed that many of these photometric candidates were genuine high-redshift objects and that their estimated masses were in the right ballpark. The JWS TCEERS survey, the Cosmic Evolution Early Release Science Survey, provided some of the first systematic data. Analysis published in early 2023 identified a population of massive galaxies at Z equals 7 through 10, whose abundance exceeded Lambda Cold Dark Matter predictions by factors of 10 to 100. These were not marginal excesses at the edge of statistical significance. They were dramatic overabundances of objects that the standard model said should barely exist. The galaxies were there. The model said they should not be. The morphologies of these early galaxies added another layer of surprise. The standard model predicted that early galaxies would be irregular and disturbed, assemblages of merging clumps rather than organized structures. Some of Webb's high-redshift galaxies did fit this picture, but others showed unexpected structural regularity. Disk-like morphologies appeared at redshifts where the universe was only 700 to 800 million years old. Some galaxies showed hints of spiral structure at epochs when the universe had not had time to build such organized systems according to any standard simulation. Organized spiral galaxies require multiple galaxy rotations to develop their characteristic arm structure through density wave instabilities. In a universe less than 1 billion years old, there should not have been enough time. The sizes of these early galaxies also surprised astronomers. Some were compact to an extraordinary degree, containing masses comparable to present-day large galaxies packed into volumes a fraction of their current size. Others were larger than expected for their mass and epoch. The distribution of sizes did not match predictions from state-of-the-art simulations. The simulations had been run on some of the most powerful computers in the world, incorporating the best available physics of gas dynamics, star formation, and feedback. They still failed to reproduce what Webb was seeing. Each individual discrepancy might be explained away. Models have free parameters. Simulations make approximations. Observations have uncertainties. But the accumulation of discrepancies, too many galaxies, too massive, too organized, with unexpected sizes and morphologies, began to look less like a collection of manageable tensions and more like evidence that something fundamental was missing from the theoretical picture. The first galaxies were not supposed to look like this. And when physics produces results that contradict its own predictions this consistently, one of two things is true. Either the observations are wrong or the theory is. JADES GSZ13 and the problem of galaxies that should not exist. In December 2022, the JADES collaboration, the JWST Advanced Deep Extragalactic Survey, published results that set the astronomical community into a quiet, productive state of alarm. The survey had targeted two of the most intensively studied patches of sky in astronomy, the Goods South and Goods North fields, using Webb's near-infrared camera for over 100 hours of combined exposure time. The resulting data set was the deepest infrared image of the universe ever obtained. And in that data, buried among thousands of faint smudges, were 4 galaxies at redshifts that pushed the frontier of the observable universe to a new limit. The most distant of these galaxies was designated Ajau RDES-GS-Z13-0. Its redshift was measured spectroscopically at Z equals 13.2, corresponding to a look-back time of approximately 13.5 billion years, and an epoch, when the universe was only about 320 million years old. This was the most distant galaxy, with a confirmed spectroscopic redshift at the time of publication, a record that itself would be broken within months as more Webb data was analysed. But the record distance was not the most alarming thing about JADES GSZ13-0. The alarming thing was what it looked like and what it implied about the physics of its formation. The galaxy was detected across multiple photometric bands, allowing its spectral energy distribution to be characterized in detail. Its ultraviolet luminosity, the light it emitted from hot, young, massive stars, was high. Surprisingly, uncomfortably high. For a galaxy existing only 320 million years after the Big Bang, it was producing stars at a rate that implied a stellar mass already accumulated to hundreds of millions of solar masses. Not enormous by the standards of present-day galaxies, but enormous for an object that had only had 320 million years to form. Consider what 320 million years means in the context of galaxy formation. Gas had to collapse into the first dark matter halos. The first stars had to ignite, live out their brief lives and die, enriching the gas around them with heavy elements. Subsequent generations of stars had to form from this enriched gas. All of this had to happen before JADES-GS-Z13-0 could even begin to look like a galaxy. And then the galaxy itself had to accumulate hundreds of millions of solar masses through star formation before the light Webb detected was emitted. The timeline is extraordinarily compressed. Fitting the observed stellar mass into the available time requires star formation efficiencies, the fraction of available gas that is converted into stars, far higher than what standard models predict. In the standard picture, star formation is an inefficient process. Feedback from massive stars, the radiation they emit, the stellar winds they drive, the supernovae they produce, heats and disperses the gas in a galaxy, limiting the rate at which new stars can form. This self-regulation keeps star formation rates modest and prevents galaxies from converting all their gas into stars too quickly. It is a well-understood physical mechanism supported by observations of nearby galaxies. In simulations of early galaxy formation, it keeps the first galaxies appropriately small and dim. To produce JADES GSZ13-0's observed stellar mass in the available time, Either the star formation efficiency was dramatically higher than standard models allow, or the galaxy began forming stars much earlier than expected. Perhaps it's Z equals 20 or beyond, in dark matter halos that should not yet have been massive enough to host significant star formation. Neither option is comfortable. Higher star formation efficiency would require that the feedback mechanisms which regulate star formation in present-day galaxies were somehow absent or suppressed in the early universe. Earlier onset of star formation would require either a revision to the dark matter model that governs when halos of sufficient mass first appear, or the presence of some non-standard process that accelerated structure formation beyond what Lambda Cold Dark Matter predicts. JADES-GS-13-0 was not alone. The same survey identified 3 other galaxies at redshifts between Z equals 10.4 and Z equals 12.5, all exhibiting similar tensions with theoretical predictions. Together, these 4 galaxies represented a population of early, massive, actively star-forming objects whose existence strained the available theoretical frameworks. The JADES team was careful in their language, as published science requires. They noted the discrepancies. They quantified the tensions. They listed the possible explanations. But the data was unambiguous. These galaxies existed. The models said objects like them should be rare to non-existent at these epochs. The models were wrong. The response from the theoretical community was rapid and productive. Within months of the JADES publication, dozens of papers appeared proposing modifications to standard galaxy formation theory that might accommodate the observations. Some invoked reduced feedback efficiency in the early universe, arguing that the first galaxies operated in a regime where stellar feedback was less effective at suppressing star formation. Some proposed modifications to the initial mass function of early stars, the distribution of stellar masses produced in a given episode of star formation, arguing that the first galaxies formed a higher proportion of massive, luminous stars than galaxies do today. Some explored the possibility that early galaxies experienced episodic bursts of star formation that temporarily made them appear more massive than their average properties would suggest. Each of these proposals has merit, and each has problems. Reduced feedback efficiency is plausible in the early universe, where metallicity, the abundance of elements heavier than hydrogen and helium, was very low. Metal-poor gas cools less efficiently than metal-rich gas, which affects the thermodynamics of star formation. But the quantitative effect of reduced metallicity on feedback efficiency is not well constrained, and the magnitude of the required reduction to explain Webb's observations is larger than most models naturally produce. A modified initial mass function could explain the high luminosities if early galaxies were producing more massive stars per unit of star-forming gas. Massive stars are far more luminous than low-mass stars, so even a modest shift toward higher masses dramatically increases a galaxy's observed brightness. But such a shift also affects the chemical enrichment of the galaxy in ways that should be detectable spectroscopically. And Webb's observations of early galaxy chemical compositions provide additional constraints that must be simultaneously satisfied. The burstiness hypothesis, that early galaxies experience violent episodes of rapid star formation followed by periods of relative quiet, is perhaps the most theoretically natural explanation. If star formation in early galaxies was highly episodic rather than steady, the galaxy's Webb court would represent objects observed during a bright phase, biasing the observed population toward unusually luminous examples. This would explain why the observed galaxies appear more massive than average, without requiring that all early galaxies were equally extreme. But it raises its own questions about what drives the episodic behavior and what the early galaxy population looks like when averaged over time. None of these explanations has yet achieved consensus. The field is in genuine ferment, with competing proposals being tested against accumulating Webb data in real time. What is clear is that JADES-GS-Z13-0 and its siblings have demonstrated that the Standard Model's predictions for the earliest observable galaxies are quantitatively wrong by amounts that require real theoretical revision. Not a tweak at the margins. A substantive rethinking of how the first structures formed in the early universe. The Hubble tension just got worse. Among the problems that existed in cosmology before Webb launched, one stood out for its stubbornness and its implications. It was called the Hubble tension, and it concerned the most fundamental measurable property of the universe, the rate at which space itself is expanding. The Hubble constant describes how fast galaxies are receding from us per unit of distance. A galaxy 1 megaparsec away, about 3.26 million light-years, recedes at a rate given by the Hubble constant in units of kilometers per second per megaparsec. Measuring this constant precisely is not merely an exercise in cosmic cartography. It is a test of the entire theoretical framework describing the universe's content and evolution. The tension arose from a discrepancy between two fundamentally different methods of measuring H0. The first method uses the early universe. The cosmic microwave background, the faint afterglow of radiation from 380,000 years after the Big Bang, when the universe first became transparent, contains a precise imprint of the acoustic oscillations that rippled through the early universe's plasma. The scale of these oscillations provides a standard ruler, and measuring how large this ruler appears on the sky tells us about the universe's geometry and expansion history. The Planck satellite, which mapped the cosmic microwave background with extraordinary precision, derived a Hubble constant of approximately 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. The second method uses the late universe. Astronomers construct what is called the cosmic distance ladder, a sequence of overlapping distance measurement techniques that progressively extend from nearby to distant objects. The foundation is parallax, the geometric shift of nearby stars against the background sky as Earth orbits the Sun. On top of this sit Cepheid variable stars, which pulsate with periods directly related to their intrinsic luminosities. Measure the period, know the luminosity, compare to the apparent brightness, and you have the distance. Cepheids are used to calibrate Type 1a supernovae, which are approximately standard candles visible across much of the observable universe. The supernova H0 for the equation of state collaboration, led by Adam Rees, used this distance ladder to measure a Hubble constant of approximately 73 kilometers per second per megaparsec, 67 versus 73, a difference of about 9%. This sounds modest until you appreciate that both measurements have uncertainties of less than 2%, making them formally inconsistent at a statistical significance of more than 5 sigma. In particle physics, 5 sigma is the threshold for declaring a discovery. In cosmology, a 5 sigma discrepancy between two fundamental measurements means that either one or both measurements has an undetected systematic error, or the standard cosmological model is missing something. Both possibilities are deeply unsettling. Before Webb, the Hubble tension was already one of the most debated problems in cosmology. Some researchers argued it was a systematic error in the distance ladder. Perhaps the Cepheid calibration was slightly off, or Type 1a supernovae were not as standard as assumed. Others argued it was a hint of new physics. Perhaps dark energy was not constant, or there was some exotic component in the early universe that modified its expansion history, or the Standard Model's assumption about the universe's content was subtly wrong. Webb entered this debate with the potential to resolve it. The telescope can observe Cepheid variable stars in galaxies far more distant than Hubble could manage, extending the distance ladder with greater precision. It can observe Cepheids in crowded stellar environments where Hubble's limited resolution produced blending effects that might have biased the calibration. If the Hubble tension was caused by a systematic error in Cepheid measurements, Webb should be able to identify and correct it. The first Webb results on the Hubble tension, published in 2023, were not the resolution that the systematic error camp had hoped for. Webb confirmed the Hubble Space Telescope's Cepheid measurements rather than correcting them downward toward the Planck value. The distance ladder Hubble constant remained firmly in the range of 72 to 73 kilometers per second per megaparsec. Webb's observations effectively ruled out the most straightforward systematic error explanations for the tension. The Cepheid measurements were not wrong in the ways that had been suggested. The discrepancy between the early universe and late universe Hubble constant measurements survived Webb's scrutiny intact. This matters enormously. A Hubble tension that survives careful independent verification by the most precise instrument ever applied to the problem is not a measurement error. It is a signal. It is the universe telling us that the standard cosmological model, the model that describes the universe's content and evolution from the Big Bang to the present, is either incomplete or incorrect. The specific nature of the missing or incorrect element remains unknown, but the possibilities being seriously discussed include early dark energy, a brief period in the early universe when the dark energy density was higher than its present value, which would have altered the acoustic oscillations in the early universe and shifted the Planck-derived Hubble constant upward. Other possibilities include modifications to the physics of recombination, the process by which the early universe's plasma became neutral and transparent, interacting dark matter models, and various forms of new physics that would alter the universe's expansion history. Webb's contribution to the Hubble tension story is therefore a negative result of the most significant kind. It did not find an error in the distance ladder. It confirmed the error-free nature of the measurement that produces the discrepant value. By doing so, it elevated the Hubble tension from a possible systematic effect to a genuine crisis in the standard model. The universe expands at a rate that depends on when you measure it, and our best theories cannot explain why. Dark matter's fingerprints are everywhere in Webb's data. Dark matter is the most abundant form of matter in the universe, comprising approximately 27% of its total energy content. It does not emit, absorb, or reflect electromagnetic radiation of any kind. It has never been directly detected in a laboratory. Its existence is inferred entirely from its gravitational effects on the orbits of stars within galaxies, on the velocities of galaxies within clusters, on the large-scale distribution of matter across cosmic space, and on the temperature fluctuations in the cosmic microwave background. Everything we know about dark matter we know through its gravitational influence on ordinary matter. Despite this indirect knowledge, dark matter is a cornerstone of modern cosmology. The Lambda Cold Dark Matter model, the standard cosmological model, gets its C from cold dark matter, meaning dark matter particles that were moving slowly relative to the speed of light in the early universe. Cold dark matter has specific, well-understood effects on structure formation. It clusters hierarchically, forming halos that grow through mergers over cosmic time. It provides the gravitational scaffolding into which ordinary matter falls to form galaxies and galaxy clusters. Without cold dark matter, the universe's large-scale structure, the web of filaments, sheets and voids traced by the distribution of galaxies, would look completely different. Webb's observations of the early universe contain dark matter's fingerprints throughout, and examining those fingerprints reveals both the successes and the failures of the cold dark matter model. On large scales, the fingerprints are reassuring. The overall distribution of early galaxies in Webb's deep fields, the way they cluster together, the filamentary structures they trace, the voids between them, is broadly consistent with what cold dark matter simulations predict. The The cosmic web, the large-scale architecture of the universe, appears to have been in place earlier than many expected, but its general character matches the predictions of Lambda Cold Dark Matter. On smaller scales, however, the picture becomes more complicated. Cold dark matter models make specific predictions about the internal structure of dark matter halos, the density profiles, the abundance of small substructure, the minimum mass of halos that can host galaxies. Some of these predictions are in tension with observations, though the severity of these tensions has been debated for years in the context of lower redshift observations. Webb now extends these questions to the early universe, where the tensions may be either amplified or resolved, depending on how physics operates in this less explored regime. One of the most direct dark matter measurements Webb enables is through gravitational lensing, the bending of light from background objects by the gravity of intervening mass. When a massive foreground galaxy or cluster lies between Earth and a more distant source, the gravity of the foreground object bends the paths of photons from the background source, distorting and sometimes magnifying its apparent image. The geometry of this distortion depends on the distribution of mass in the foreground object, including the dark matter that dominates the mass budget. By measuring how background galaxies are distorted, astronomers can map the dark matter distribution in intervening structures with precision that no other technique can match. Webb's resolution and sensitivity make it an extraordinarily powerful gravitational lensing instrument. Its early observations of galaxy clusters used as gravitational lenses revealed dark matter distributions with a level of detail that exposed subtle discrepancies with cold, dark matter predictions. The concentrations of dark matter in cluster cores, the central density peaks, appeared in some cases higher than simulations predicted. In other cases, the substructure within cluster halos, the population of smaller dark matter clumps orbiting within larger halos, showed properties that challenged the smooth distributions produced by standard cold dark matter models. These small-scale tensions are not new. For years, observations of nearby galaxies and dwarf galaxies have suggested that cold dark matter halos have different internal structures than simulations predict, a problem known as the core cusp tension. Cold dark matter simulations produce halos with density profiles that rise steeply toward the center, called cusps. Observations of many real galaxies suggest that dark matter distributions are more uniform near the center, called cores. Whether this represents a failure of the cold dark matter model or a consequence of baryonic physics, the effects of ordinary matter, star formation, and feedback on dark matter distributions has been debated inconclusively for decades. Webb's observations of early universe galaxies, where baryonic feedback processes were different than in present-day galaxies, provide a new testing ground for these competing explanations. If the core cusp tension persists in early universe galaxies where feedback was operating differently, it becomes harder to explain as purely a baryonic effect and more suggestive of a genuine modification to the dark matter model. Preliminary Webb data suggests the tension does persist at high redshift, though the sample sizes are currently too small for definitive conclusions. The most dramatic dark matter story in Webb's early observations involves gravitational lensing magnification. Webb has detected galaxies at extreme redshifts that were only observable because they were gravitationally magnified by foreground mass concentrations. The magnification acts as a natural telescope, amplifying the brightness of distant objects and allowing Webb to detect them when they would otherwise be too faint. By measuring the magnification factors, which depend on the dark matter distribution in the lensing structure, Webb simultaneously learns about the dark matter and the distant galaxy. The highest redshift confirmed galaxies in Webb's sample owe their detectability partly to this dark matter-assisted amplification. Dark matter's gravitational scaffolding is what made the early universe's structure possible. Without it, ordinary matter would not have had the gravitational seeds it needed to condense into the first galaxies. The very existence of the objects Webb observes at z equals 13 is a confirmation of dark matter's role in cosmic structure formation. But the details of that role, the precise properties of dark matter particles, the exact behavior of dark matter halos on small scales, the relationship between dark matter structure and galaxy formation efficiency remain genuinely uncertain. And Webb's data is actively shaping the debate about which dark matter model best describes the universe. Reionization was not the clean event we thought it was. In the beginning, the universe was opaque. For the first 380,000 years after the Big Bang, the cosmos was so hot and dense that photons could not travel freely. They were constantly scattered by the free electrons that permeated the plasma, filling everything. Then, as the universe cooled, electrons and protons combined to form neutral hydrogen atoms, and the universe became transparent for the first time. This event, called recombination, is when the cosmic microwave background radiation was released, the ancient afterglow of the Big Bang that forms the backdrop against which all of modern cosmology is built. After recombination, the universe entered what cosmologists call the cosmic dark ages. There were no stars, no galaxies, no sources of light. The universe was filled with cold, neutral hydrogen gas and dark matter halos slowly growing through gravitational attraction. For perhaps 200 to 400 million years, the universe was truly dark. No photons were being emitted by any source bright enough to change this state. And then the first stars ignited, and everything changed again. The ultraviolet light from the first stars and galaxies was energetic enough to ionize the neutral hydrogen that surrounded them, to strip the electron from each hydrogen atom and return it to the free state that had existed before recombination. This process, called reionization, gradually transformed the universe's hydrogen from neutral to ionized, clearing the cosmic fog and making the universe transparent to ultraviolet light for the first time since recombination. Reionization is the most dramatic phase transition the universe has undergone since the Big Bang, and understanding when it happened, how long it took, and what drove it is one of the central questions of observational cosmology. The standard picture of reionization, developed from observations available before Webb, described a relatively gradual and somewhat uniform process. Galaxies in the early universe emitted ultraviolet photons that created expanding bubbles of ionized hydrogen around them. Over time, these bubbles grew and merged, eventually overlapping and completing the reionization of the universe by about z equals 6, roughly 900 million years after the Big Bang. The process took several hundred million years and was driven primarily by star-forming galaxies, with possible contributions from quasars and other energetic sources. This picture had the virtue of consistency with available data, but the data before Webb was limited. The key probe of reionization is the Lyman alpha emission line of hydrogen, produced when electrons in hydrogen atoms transition from their second energy level to their lowest level, releasing a photon at a specific ultraviolet wavelength that gets redshifted into the visible or near infrared for distant sources. This emission line is produced prolifically by star-forming galaxies, and its detectability provides information about the neutral hydrogen fraction of the intergalactic medium along the line of sight. Neutral hydrogen absorbs Lyman alpha photons efficiently, so a high neutral fraction produces a characteristic suppression of Lyman alpha emission from background sources. Before Webb, measurements of the Lyman alpha emission from galaxies between z equals 6 and z equals 8 provided the primary constraints on when reionization completed and how rapidly the neutral fraction declined. These measurements suggested that reionization completed relatively rapidly, the neutral fraction dropping from perhaps 50% at z equals 8 to near 0 by z equals 6 over only a few hundred million years. The process appeared reasonably clean. Galaxies formed, ionized their surroundings, bubbles merged, and by about 900 million years after the Big Bang, the universe was fully ionized. Webb's observations have complicated this picture substantially. The telescope's ability to detect Lyman alpha emission from galaxies at Z equals 7 to 10 with unprecedented sensitivity revealed a patchy, inhomogeneous reionization process quite different from the smooth, gradual transition of the standard picture. Some regions of the early universe appear to have been reionized much earlier than others. Some lines of sight show Lyman alpha emission from galaxies at Z equals 8 or 9, where the intergalactic medium appears already largely ionized, while other sight lines at similar redshifts show strong suppression consistent with a predominantly neutral medium. This patchiness is not entirely surprising. Theoretical models predicted some inhomogeneity in reionization driven by the clustered nature of early galaxies. But the amplitude of the variation Webb is detecting suggests more extreme patchiness than most models anticipated. Some regions of the universe at Z equals 8 appear to have been almost fully reionized, while adjacent regions remain predominantly neutral. The size scales of these ionized bubbles and neutral regions carry information about the nature of the ionizing sources and the topology of reionization that is only now becoming observable. Webb also detected unexpectedly bright Lyman alpha emission from some of the most distant galaxies in its sample, objects at Z equals 11 and beyond, where the intergalactic medium should have been largely neutral according to the standard timeline, and where Lyman alpha photons should have been heavily absorbed. The detection of bright Lyman alpha from such early, distant galaxies suggests that some individual galaxies managed to carve out large ionized bubbles in their immediate environments, creating local pockets of transparency in an otherwise neutral universe. The ionizing photon budget for such large bubbles requires either extraordinary star formation rates in the observed galaxies or the presence of additional ionizing sources, possibly faint galaxies too dim for even Webb to detect individually, but contributing collectively to the local ionization. The implications for the reionization timeline are significant. If large ionized bubbles existed as early as Z equals 11 or 12 in some regions, while other regions remain neutral until Z equals 6 or later, then reionization was a more extended and more chaotic process than the standard picture described. The start of reionization may have occurred earlier than previously thought, driven by rare but extremely luminous early galaxies creating initial pockets of ionized gas hundreds of millions of years before the bulk of the universe was reionized. The end of reionization may have occurred later in some overdense neutral regions that were shielded from ionizing photons by their high density. This extended, patchy reionization creates a different cosmic environment for the early galaxies Webb observes than the standard picture assumed. Galaxies in large ionized bubbles would have experienced very different conditions from galaxies surrounded by neutral gas. Feedback from the ionizing radiation would affect gas cooling, star formation, and galaxy growth differently in different environments. Models that assumed a uniform reionization history need to be replaced with models that track the spatial and temporal variation in the ionization state of the intergalactic medium. A far more computationally demanding and theoretically complex undertaking. Supermassive black holes were already enormous at the beginning of time. One of the most persistent and productive puzzles in astrophysics concerns the origin and growth of supermassive black holes. We know that supermassive black holes, objects containing millions to billions of solar masses, inhabit the centers of essentially all large galaxies today. We know that some of these black holes were already extraordinarily massive within the first billion years of cosmic history, because quasars, the intensely luminous signatures of actively accreting supermassive black holes, are observed at redshifts of Z equals 6 and beyond. The most massive quasar-host black holes detected before Webb at these early epochs contained more than 1 billion solar masses, accumulated in less than 1 billion years. How a black hole can grow to 1 billion solar masses in less than 1 billion years is a serious theoretical problem. The maximum rate at which a black hole can accrete mass, the Eddington limit, set by the balance between radiation pressure, pushing outward, and gravity pulling inward, limits growth to a characteristic doubling time of roughly 45 million years under optimal conditions. Starting from a black hole of 100 solar masses, which is approximately the maximum mass remnant from the collapse of a single massive star, exponential growth at the Eddington rate requires about 800 million years to reach 1 billion solar masses. This is tight, but technically possible if the black hole accretes continuously at its maximum rate, a demanding and unlikely assumption, since black holes are not expected to sustain Eddington accretion for hundreds of millions of years without interruption. The required continuous Eddington accretion has always made theorists uncomfortable. Real black holes in the modern universe rarely sustain Eddington rate accretion for more than short episodes. The gas supply is typically insufficient. The feedback from the accreting black hole itself heats and disperses surrounding gas, and the overall efficiency of the process is far below what would be needed for sustained maximum rate growth. The existence of billion solar mass black holes at Z equals 6 was already pushing the limits of what standard black hole growth models could accommodate. Webb extended the problem. In its first year of science operations, the telescope discovered active supermassive black holes at redshifts of Z equals 8, 9 and beyond, at epochs when the universe was only 600 to 700 million years old. Some of these objects, detected through their broad emission lines in Webb spectroscopy, appear to host black holes of tens of millions to hundreds of millions of solar masses. This is less massive than the most extreme Z equals 6 quasars, but more alarming in a different way, because these black holes exist at even earlier times, further compressing the available growth time. A black hole of 100 million solar masses at Z equals 9 existed when the universe was only about 550 million years old. Working backwards, this object had to grow from some seed to 100 million solar masses in 500 million years or less. Starting from a stellar mass seed of 100 solar masses, achieving this requires growth at rates that exceed the Eddington limit for significant periods, so-called super Eddington accretion, or starting from a much more massive seed that bypasses the slow early growth phase entirely. Super Eddington accretion is theoretically possible and has been invoked to explain the most extreme high-redshift quasars. The physics of accretion at rates exceeding the Eddington limit is complex and not fully understood, but simulations suggest it can occur in specific geometric configurations where the accretion disk is geometrically thick and radiation escapes preferentially along polar directions rather than uniformly. The radiative efficiency in super Eddington accretion is lower than in Eddington limited accretion, meaning more of the infalling mass is retained in the black hole rather than being radiated away, which accelerates growth. But sustaining super Eddington accretion for hundreds of millions of years requires a continuous, generous gas supply that is difficult to arrange in theoretical models of the early universe. The alternative, more massive seeds, brings its own complications. There are two serious candidates for massive black hole seeds in the early universe. The first is the direct collapse black hole scenario. In this model, under specific conditions in the early universe, a massive gas cloud collapses directly into a black hole of 10,000 to 100,000 solar masses without first forming normal stars. The conditions required are stringent. The gas must be metal-free hydrogen and helium. It must be exposed to a sufficiently strong radiation field that prevents the cooling processes that would normally cause it to fragment into stars, and the right level of turbulence must be present. Whether these conditions occurred often enough in the early universe to produce a significant population of direct collapse seeds is uncertain. The second candidate is runaway stellar mergers in the dense cores of early star clusters. If a star cluster is sufficiently dense, stars can collide and merge faster than they evolve off the main sequence, building a very massive star of thousands of solar masses. This very massive star then collapses into an intermediate mass black hole that can serve as a seed for further growth. Webb's detection of candidate intermediate mass black holes in the galactic center, as noted in the reference material, suggests this channel may operate in dense stellar environments. If it operated efficiently in the early universe, it could produce seeds massive enough to grow into the black holes Webb is detecting at Z equals 8 and 9 without requiring sustained super Eddington accretion. Webb is not merely finding massive black holes at high redshift. It is finding them in places and with properties that constrain the full range of theoretical options in new ways. Several of the high redshift black holes Webb detected appear to be overmassive relative to their host galaxies, meaning the ratio of black hole mass to stellar mass in the galaxy is much higher than the approximately 0.1 to 0.2% ratio observed in present-day galaxies. If these early black holes are genuinely overmassive, it suggests that black hole growth preceded galaxy growth in the early universe, with the black hole accumulating most of its mass before the host galaxy built up its stellar content. This inverts the conventional picture derived from low redshift observations in which black hole growth and galaxy growth are roughly synchronized through co-evolutionary feedback processes. The overmassive early black holes, if confirmed by larger samples and more detailed analysis, would require a fundamental revision of the co-evolution picture. Either the standard mechanisms coupling black hole growth to host galaxy growth operated differently in the early universe, or different growth pathways dominated at high redshift that have since been replaced by the co-evolutionary processes observed locally. Either way, the black holes Webb is finding at the edge of the observable universe are reshaping our understanding of how these monsters and their host galaxies grew together across cosmic time. The cosmic web is older and more structured than any model predicted. The large-scale structure of the universe is one of the most striking features of the cosmos viewed from a sufficient distance. Galaxies do not distribute randomly through space. They cluster along filaments, enormous tendrils of matter stretching for hundreds of millions of light years, that intersect at nodes where galaxy clusters accumulate. Between these filaments lie vast voids nearly empty of galaxies, spanning hundreds of millions of light years across. The overall pattern, filaments, sheets, nodes, and voids, is called the cosmic web, and it represents the gravitational architecture of the universe as built by the interaction of dark matter, ordinary matter, and the universe's expansion over cosmic time. The cosmic web emerges naturally from tiny density fluctuations present in the early universe. These fluctuations, which are imprinted in the cosmic microwave background as temperature variations at the level of 1 part in 100,000, were the seeds from which all structure grew. Under gravity, overdense regions attracted more matter and grew denser, while underdense regions lost matter and grew emptier. The initially subtle density contrasts amplified over billions of years into the dramatic architecture of filaments and voids we observe today. The timing and character of this amplification is precisely what the Lambda Cold Dark Matter model describes, and the large-scale structure of the present-day universe is one of the model's great successes. The cosmic web we observe matches Lambda Cold Dark Matter predictions remarkably well on scales from tens to hundreds of megaparsecs. Webb's observations of the high redshift universe ask whether this match persists at early cosmic times when the density contrasts were supposed to be still small and the cosmic web still in the process of assembly. The answer, in several documented cases, has been surprising. Webb has identified structures at redshifts of Z equals 7 and beyond that appear to be protoclusters. overdense regions that are the progenitors of present-day massive galaxy clusters, at earlier stages of assembly than standard models predict for such concentrated structures. The most dramatic example discovered in early Webb observations was a protocluster at approximately Z equals 7.9, existing about 700 million years after the Big Bang. This structure contained a significant overdensity of galaxies in a relatively small volume, suggesting that gravitational collapse had already proceeded to a degree of organization that Lambda Cold Dark Matter simulations suggest should not have occurred by that epoch. The galaxies in the protocluster showed coherent velocities consistent with gravitational infall into a common potential well, a signature of organized large-scale structure rather than a random assemblage. At Z equals 7.9, the universe had only recently completed or was still completing the reionization process. The density fluctuations that seeded structure formation had been growing for only 700 million years. For a protocluster to have assembled the degree of organization Webb observed at this epoch, either the initial density fluctuations were larger than the cosmic microwave background measurements suggest, or the growth of structure was somehow accelerated relative to standard predictions. The former option, larger initial fluctuations, conflicts with the extraordinarily precise measurements of the cosmic microwave background by the Planck satellite. The fluctuation spectrum is constrained to better than 1% precision at the angular scales relevant to cluster formation. There is no room in the Planck data for fluctuations large enough to explain premature structure formation without also producing other effects that would conflict with observations. The latter option, accelerated structure growth, could arise from modifications to the dark matter model, from additional attractive forces operating on cosmological scales, or from a different expansion history than Lambda Cold Dark Matter assumes. Webb also found evidence for large-scale coherent structures at high redshift in the form of galaxy alignments and correlated properties extending over surprisingly large scales. Multiple galaxies at similar redshifts showed correlated colors, morphologies, and star formation properties in ways that suggest they were influenced by the same large-scale environment, the local node in the cosmic web, even before the individual galaxies had interacted directly. These large-scale correlations implied that the cosmic web was already exerting observable environmental influences on galaxy formation at epochs when it should have been far less developed than at present. The implications for galaxy formation theory are substantial. If the cosmic web was already structuring galaxy evolution at Z equals 8 and beyond, models that treat early galaxies as isolated objects forming independently within their individual dark matter halos are fundamentally incomplete. The environment, the local density, the filamentary structure, the proximity to forming clusters, was already shaping galaxy properties in the first billion years of cosmic history. Models that neglect environmental effects at these early epochs will systematically fail to reproduce the observations, and the degree to which environment was important at high redshift is only now becoming observationally accessible through Webb. Star formation in the early universe broke every rule we had. Star formation is the engine of galaxy evolution. Every galaxy we observe, including our own Milky Way, grew to its current state through the repeated transformation of gas into stars across billions of years. The rate at which a galaxy forms stars, the efficiency with which it converts available gas into stellar mass, and the properties of the stars it produces all determine the galaxy's luminosity, color, chemical composition, and eventual fate. Understanding star formation is therefore not peripheral to galaxy formation theory. It is central to it. The rules governing star formation in the present-day universe are reasonably well established, at least in broad strokes. Gas cools in dark matter halos and condenses into molecular clouds. Within these clouds, regions of sufficient density collapse under their own gravity to form protostars. Feedback from the stars themselves, radiation, stellar winds, supernovae, heats and disperses surrounding gas, limiting the fraction of available gas that is converted into stars, and regulating the star formation rate. The overall efficiency of star formation, the fraction of a galaxy's available baryons that end up in stars over its lifetime, is observed in present-day galaxies to be roughly a few percent, a low value reflecting the effectiveness of stellar feedback in suppressing star formation. These rules were derived from observations of nearby galaxies and validated against simulations. They were then extrapolated to high redshift to predict how early galaxies should behave. The extrapolation produced specific quantitative predictions. Star formation rates as a function of galaxy mass and redshift. The relation between a galaxy's stellar mass and its current star formation rate. The timescale over which galaxies convert their gas into stars. These predictions are the backbone of any serious model of galaxy evolution, and they are what Webb tested directly for the first time at the extreme redshifts accessible only to its infrared instruments. The tests failed, not catastrophically across the board, but in enough specific ways and with enough consistency to constitute a serious challenge. Star formation in the early universe was more efficient, more violent, and in some cases faster than any rule derived from nearby galaxies would predict. The specific star formation rates, star formation per unit of stellar mass already present, observed in many high redshift Webb galaxies exceed present-day values by factors of 10 to 100. This is expected to some degree. The early universe had more available gas and less built-up stellar mass, both of which drive higher specific star formation rates. But the magnitude of the excess in the most active early galaxies is larger than standard models produce. The distribution of star formation rates at high redshift also showed unexpected features. The standard model predicts a relatively narrow distribution centered on a characteristic star formation rate for galaxies of a given mass and redshift, the so-called main sequence of star-forming galaxies. Galaxies are expected to cluster along this main sequence, with deviations caused by merger-induced starbursts or feedback-driven quenching. Webb's observations of high redshift galaxies revealed a wider distribution than predicted, with a significant population of galaxies forming stars at rates far above the expected main sequence. These starburst galaxies in the early universe were forming stars with furious efficiency, converting available gas into stars at rates that would exhaust their entire gas supply in only a few tens of millions of years. In the present universe, galaxies sustain star formation over billions of years through a balance between gas consumption and gas replenishment from the cosmic web. The early starburst galaxies Webb found had no such balance. They were burning through their gas with a profligacy that the standard regulatory mechanisms should have prevented. The physical conditions in these early starbursts were also extreme by present-day standards. Webb's spectroscopy revealed that the star-forming gas in early galaxies was hotter, denser, and more turbulent than the gas in comparable present-day galaxies. The interstellar radiation field, the bath of ultraviolet photons from young stars pervading the star-forming regions, was more intense. The ionization conditions were more extreme. The early universe's star-forming regions were more violent environments than their present-day counterparts, and the stars they produced may have reflected these conditions through properties different from those of stars forming today. The most unexpected finding about early star formation was its possible efficiency even in the smallest, least massive galaxies. Standard models predict that feedback from supernovae should be particularly effective at suppressing star formation in low-mass galaxies, where the shallow gravitational potential well allows supernova-heated gas to escape the galaxy entirely. This feedback should keep low-mass galaxies in the early universe dim and gas-rich. Webb found several examples of low-mass early galaxies, with star formation efficiencies far higher than this picture would allow, suggesting that either supernova feedback was less effective at early times, or that these small galaxies had some additional mechanism for retaining their gas and sustaining star formation despite the energetic input from stellar explosions. The combined picture emerging from Webb's star formation observations is of an early universe where galaxies formed stars more efficiently, more violently, and in some cases faster than any model derived from present-day observations would predict. The rules of star formation appear to have been different in the early universe, not so different as to require abandoning the basic physics, but different enough in their quantitative behavior that models calibrated on nearby galaxies systematically underpredict the star formation activity Webb observes at high redshift. The early universe was a more extreme environment than we gave it credit for, and the stars and galaxies it built reflected that extremity in their properties. The universe's chemical timeline has been completely rewritten. Every atom of carbon in your body was forged inside a star. Every atom of oxygen you breathe was produced by nuclear fusion in a stellar interior and scattered into space when that star died. The iron in your blood was synthesized in the final moments of a massive star's collapse, released in the violence of a supernova explosion. The universe began with essentially only hydrogen and helium, the two lightest elements produced in the first 3 minutes after the Big Bang through a process called Big Bang nucleosynthesis. Every element heavier than helium, everything on the periodic table from lithium to uranium, was built by stars across cosmic time through the slow generational process of stellar nucleosynthesis. This process has a timeline. It takes time to build heavy elements. The first stars had to form from pure hydrogen and helium, live out their lives, and die before any significant quantity of carbon, oxygen, nitrogen, or iron existed in the universe. The second generation of stars formed from gas enriched by those first stellar deaths, building more heavy elements through their own nuclear fires. Each generation added to the cosmic inventory of elements, gradually enriching the universe's chemical composition over billions of years. This is why astronomers use metallicity, the abundance of elements heavier than helium, collectively called metals in astronomical terminology, as a proxy for age. Old stellar populations have low metallicity. Young stellar populations have high metallicity. The universe's metal content has been increasing monotonically since the first stars died. This chemical timeline was one of the most confidently constrained aspects of standard galaxy formation theory. Simulations predicted how the metallicity of galaxies should evolve with redshift, a steady decline as you look back to earlier epochs, reflecting the progressive depletion of heavy elements with decreasing cosmic age. The relationship between a galaxy's stellar mass and its metallicity, the mass-metallicity relation, was predicted to evolve in a specific way, with higher redshift galaxies of a given mass being systematically more metal poor than their low redshift counterparts. These predictions had been tested and largely confirmed by observations of galaxies out to z equals 3 or 4 using ground-based telescopes. Webb was expected to extend these tests to higher redshifts and confirm that the chemical evolution picture held at the earliest accessible epochs. Webb's spectroscopic observations of high redshift galaxies revealed that the chemical timeline was not as neat as the models described. Some early galaxies were more metal-rich than expected for their redshift and mass. Galaxies at z equals 7 and 8 showed metallicities that were inconsistent with the slow, generational buildup of heavy elements that standard models predicted. If those galaxies contained the metal abundances Webb's spectroscopy indicated, they had to have been processing gas through stellar birth and death cycles for longer than the available cosmic time seemed to allow, or they had to be doing so with an efficiency that standard stellar evolution models could not accommodate. The most dramatic chemical surprises came from Webb's detections of specific molecules and ionic species in early galaxies that had not been expected to be detectable at these redshifts. Carbon emission lines, which trace the carbon abundance in star-forming gas, appeared in galaxies at Z equals 8 and beyond at strengths suggesting carbon abundances significantly higher than models predicted. Carbon is produced primarily in intermediate mass stars that take hundreds of millions to a few billion years to evolve off the main sequence and release their carbon into the interstellar medium. Finding substantial carbon abundances in galaxies only 700 to 800 million years old implied either that intermediate mass stars were evolving faster than standard stellar evolution theory allows, or that the initial mass function of early star formation was weighted toward the intermediate masses responsible for carbon production, or that some other mechanism was enriching the early universe with carbon faster than the standard model accommodates. Nitrogen presented an even sharper puzzle. Webb detected unexpectedly strong nitrogen emission in several high-redshift galaxies, including some at Z equals 10 and beyond. Nitrogen is produced through a complex chain of nucleosynthetic processes involving both massive stars and lower mass stars, and its abundance relative to other elements like oxygen carries information about the stellar populations responsible for chemical enrichment. The nitrogen to oxygen ratios Webb measured in some early galaxies were higher than any simple model of chemical evolution could produce in the available time. High nitrogen to oxygen ratios are normally associated with galaxies that have undergone extended periods of star formation, allowing lower mass stars sufficient time to release their nitrogen. In galaxies only a few hundred million years old, these ratios should be negligible. One possibility is that the high nitrogen abundances reflect enrichment from Wolf-Rayet stars, massive stars in a brief evolutionary phase, during which they shed their outer layers in intense stellar winds, releasing nitrogen-rich material into the surrounding gas. Wolf-Rayet stars can enrich their environments on timescales of only a few million years, fast enough to explain elevated nitrogen in young galaxies. But the magnitude of the enrichment Webb observed in some cases exceeds what Wolf-Rayet stars alone are expected to produce, requiring either an unusually high fraction of Wolf-Rayet stars in early galaxies, or some additional nitrogen source not captured in standard chemical evolution models. The oxygen abundance in early galaxies provided further complications. Oxygen is the most abundant heavy element in the universe, produced primarily by massive stars on timescales of only a few million years. The oxygen to hydrogen ratio in a galaxy's gas is therefore a relatively direct indicator of how many generations of massive stars it has processed. Webb found a wide range of oxygen abundances in early galaxies, from very low values consistent with the expected primitive chemical state to surprisingly high values that implied substantial prior chemical enrichment. The scatter in the mass metallicity relation at high redshift appears to be larger than at low redshift, suggesting that early galaxy chemical evolution was more diverse and less predictable than the smooth evolutionary tracks of standard models assumed. This chemical diversity in the early universe is itself informative. It suggests that the efficiency and timing of chemical enrichment varied dramatically from galaxy to galaxy at high redshift, driven by differences in star formation history, merger activity, gas inflows and outflows, and the initial conditions of each galaxy's formation environment. Some early galaxies had already processed substantial amounts of gas through stars and accumulated significant metal abundances. Others, forming at similar epochs, remained chemically primitive. The universe's chemical timeline was not a single universal clock ticking at the same rate everywhere. It was a collection of local clocks running at different speeds, determined by local conditions. A picture that is physically reasonable, but considerably more complex than the clean evolutionary sequences that theoretical models typically describe. Dead galaxies at the dawn of time make no physical sense. Among the most genuinely disturbing findings from Webb's early science operations was the discovery of massive galaxies at high redshift that had already stopped forming stars. In the language of observational astronomy, these are called quiescent galaxies, objects whose star formation has been shut down, whose stellar populations are aging and growing redder, and whose gas supply has either been consumed, expelled, or otherwise rendered unavailable for new star formation. Quiescent galaxies in the present-day universe are common. Elliptical galaxies, which dominate the population of the most massive present-day galaxies, are almost entirely quiescent. They formed the bulk of their stars billions of years ago and have been passively aging ever since. The existence of quiescent galaxies in the present-day universe is well understood, or at least well described. Active galactic nuclei feedback, in which energy from an accreting supermassive black hole heats and expels a galaxy's gas, is the leading mechanism for shutting down star formation in massive galaxies. Galaxy mergers, which can trigger starbursts that rapidly consume available gas, also contribute. The halo quenching mechanism, in which gas falling into very massive dark matter halos is shock heated to temperatures that prevent it from cooling efficiently, plays a role at the highest masses. These mechanisms operate over timescales of hundreds of millions to a few billion years and are calibrated against the quiescent galaxy population in the low redshift universe. Before Webb, quiescent galaxies had been identified at redshifts up to about Z equals 4 or 5, epochs when the universe was between 1 and 2 billion years old. These objects were already puzzling because they required their star formation to have been both vigorous enough to build substantial stellar masses quickly and then shut down rapidly enough to be already quiescent by Z equals 4. Explaining them required invoking the most efficient versions of the quenching mechanisms listed above, operating at the edges of what was theoretically comfortable. The existence of post-starburst galaxies at Z equals 4, objects that had clearly undergone a recent burst of star formation followed by rapid quenching, was one of the more challenging features of the pre-Webb observational landscape. Webb found quiescent galaxies at Z equals 5, 6, and in some photometric candidates, potentially higher. These objects existed when the universe was less than a billion years old. A galaxy at Z equals 6 that is already quiescent has accomplished something that the standard model finds extraordinarily difficult to explain. It formed most of its stellar mass rapidly, then shut down star formation, and was already in a passively aging state within the first billion years of cosmic history. The timeline problem is severe. To be quiescent at Z equals 6, a galaxy must have undergone rapid star formation at Z equals 8 or 10 or beyond, converting a substantial amount of gas into stars quickly. This is already the same problem as the overly massive early galaxies. The efficiency required exceeds standard predictions. But then, in addition to the formation problem, the galaxy must have had its star formation quenched by some mechanism operating within only a few 100 million years. The mechanisms that quench star formation in the low redshift universe are not known to operate on such short timescales. AGN feedback, the most efficient quenching mechanism in standard models, typically operates over hundreds of millions of years as the central black hole grows to sufficient mass, and its energy output begins to regulate the host galaxy's gas supply. To quench a galaxy at Z equals 8 so that it is observably dead by Z equals 6 requires either a faster version of known quenching mechanisms or a mechanism not currently incorporated in standard models. Some theoretical proposals invoke a particularly violent phase of AGN feedback at high redshift, driven by supermassive black holes that were overmassive relative to their host galaxies. Exactly the overmassive black holes that Webb has independently detected. If the black hole to stellar mass ratio was much higher in early galaxies than in present-day ones, the AGN might have been capable of driving more energetic outflows relative to the host galaxy's potential well, making quenching faster and more complete. This creates an interesting potential connection between the overmassive black hole problem and the early quenching problem. Both might be symptoms of the same underlying difference between early and present-day galaxy formation. Other proposals involve the rapid consumption of gas through extraordinarily intense star formation, so vigorous that the galaxy depletes its entire gas supply within a few 100 million years, after which star formation simply stops for lack of fuel. This scenario requires star formation efficiencies even higher than those already needed to explain the massive early galaxies, pushing the theoretical framework further into territory where standard feedback models struggled to maintain self-consistency. If galaxies are forming stars fast enough to exhaust their gas in hundreds of millions of years, while simultaneously resisting the supernova feedback that should disrupt the star-forming gas, some physical mechanism must be suppressing feedback in the early universe to a degree that nothing in our current models produces naturally. The environmental quenching mechanism, in which a galaxy's gas supply is cut off by its host dark matter halo or its position within the cosmic web, has been explored as a possible early quenching agent. But this mechanism is typically slower and less efficient at high redshift, where the cosmic web is less developed and halos are less massive. Strangulation, in which a galaxy's supply of cold gas from the intergalactic medium is gradually shut off, operates on timescales of billions of years in present-day environments and cannot easily be compressed to the hundreds of millions of years required to produce quiescent galaxies at z equals 6. The dead galaxies, Webb found at the dawn of cosmic time, are not merely challenging for galaxy formation theory. They are challenging for the overall structure of the standard cosmological model, because they require both an efficient formation mechanism and a rapid quenching mechanism to operate sequentially within a compressed time frame that the model's physics struggles to fill. They are, in the words of several published analyses, galaxies that should not exist at the epochs where Webb finds them. That they do exist is not in question. The data is clear, the spectroscopic conformations are solid, and the passive spectral signatures of these dead early galaxies are unmistakable. The question is what we are missing in our understanding of the physical processes that made them. Webb found light that travelled 13.8 billion years to reach us. There is something philosophically vertiginous about what Webb does when it collects light from the edge of the observable universe. A photon detected by Webb's instruments from a galaxy at z equals 13 has been travelling since the universe was only 320 million years old. It was emitted by a star or a gas cloud that no longer exists in the form it had when the emission occurred. The galaxy that contained that star has had 13.5 billion years to evolve, merge with other galaxies, be stripped apart by larger structures, or otherwise transform into something completely unrecognizable from what it was at the moment of emission. The photon itself, meanwhile, has been traveling through expanding space, its wavelength stretched from ultraviolet to infrared by the universe's growth, for nearly the entire age of the cosmos before entering Webb's mirror. This is not merely a poetic observation. It has concrete scientific implications that affect how Webb's observations must be interpreted. When we observe a galaxy at z equals 13, we are not observing the galaxy as it currently is. We are observing a snapshot of what it was 13.5 billion years ago. The galaxy's current state, if indeed any recognizable descendant of it still exists, is completely unknown to us and unknowable by any current means. The light carrying information about its present condition has not yet had time to reach us. We are, in a very precise and literal sense, observing the past. The most distant confirmed source in Webb's catalogue at the time of writing was a galaxy candidate with a photometric redshift suggesting Z equals approximately 16.4, corresponding to a universe perhaps 230 million years old. If confirmed spectroscopically, this object would have been observable when the universe was less than 2% of its current age, when the first stars were barely beginning to form, and the process of reionization had not yet begun. The light we would be collecting from such an object has been travelling for approximately 13.6 billion years, longer than the age of our Sun, by a factor of 3. Webb's deepest observations revealed a universe at epochs when the physical conditions were so different from today that essentially none of the familiar context of present-day astrophysics applies. There was no molecular oxygen in the early universe. It had not yet been synthesized. There was no significant dust, because dust grains require heavy elements to form, and heavy elements required stars to produce them. The intergalactic medium was still largely neutral, its reionization incomplete. The cosmic microwave background, now faintly glowing at 2.7 degrees above absolute zero, was at these epochs still warm enough to affect the physics of gas cooling and star formation. The universe's density was orders of magnitude higher than today, with all the implications that carries for collision rates, merger rates, and the pace of gravitational structure formation. The light from these extreme distances carries not just information about individual galaxies, but information about the physical state of the universe as a whole at those epochs. The opacity of the intergalactic medium to Lyman alpha photons tells us the neutral hydrogen fraction. The clustering of sources tells us about the dark matter distribution. The chemical composition of emitting gas traces the nucleosynthetic history. Every photon from the cosmic frontier is simultaneously a measurement of the object that emitted it and a measurement of everything that photon passed through during its 13 billion year journey. Webb's ability to detect and spectroscopically analyze these ancient photons represents a technical achievement that deserves its own moment of appreciation before returning to the scientific implications. The photons arriving from a galaxy at Z equals 13 carry approximately 1 trillionth the energy per photon of the light from a nearby star. Detecting them requires not just a large mirror and sensitive detectors, but the ability to distinguish these faint signals from the thermal noise of the detector itself, from zodiacal light scattered by dust in our solar system, from the diffuse infrared glow of our own galaxy, and from the contaminating signals of nearby foreground galaxies that overlap on the sky with the distant targets. Webb's engineering solved all of these challenges simultaneously, achieving sensitivities that were targets of aspiration rather than confident expectation when the telescope was first proposed in the 1990s. The scientific harvest from this sensitivity has been a cascade of discoveries that individually would have defined careers and collectively are reshaping a scientific field. In its first 2 years of science operations, Webb detected more confirmed galaxy candidates at Z greater than 10 than all previous telescopes combined had identified in 4 decades of effort. It produced spectroscopic confirmations of objects at redshifts that were merely photometric estimates 6 months prior. It measured chemical compositions, ionization conditions, stellar populations, and morphologies for galaxies that previous instruments could barely detect as single pixels of light. The edge of the observable universe is not a static boundary. As Webb accumulates more observing time, as its data is analysed by an expanding community of astronomers, and as its instruments reveal new objects in fields that have been observed multiple times, the frontier moves incrementally outward. Each new record-breaking redshift confirms both the telescope's extraordinary capability and the richness of the early universe that capability is exposing. The light that has travelled farthest to reach us carries the oldest stories in the cosmos, and Webb is reading them for the first time. The standard model of cosmology is under serious pressure. The Lambda Cold Dark Matter model is the most successful theoretical framework in the history of cosmology. It describes the universe's content as approximately 5% ordinary matter, 27% cold dark matter, and 68% dark energy in the form of a cosmological constant lambda. It describes the universe as having originated in a hot, dense Big Bang approximately 13.8 billion years ago, followed by a brief period of exponential expansion called inflation that smoothed out the initial conditions and planted the seeds of all future structure. It predicts the acoustic oscillation pattern of the cosmic microwave background with extraordinary precision. It correctly describes the large-scale distribution of galaxies. It predicts the abundance of galaxy clusters as a function of mass and redshift. It accommodates the accelerating expansion of the universe revealed by Type 1a supernova observations in 1998. For 3 decades, it has been tested by increasingly precise observations and has passed test after test. And yet, by the time of Webb's first science results, Lambda Cold Dark Matter was already showing signs of strain that had nothing to do with the telescope. The Hubble tension was perhaps the most discussed, but it was not alone. The S8 tension concerned the amplitude of matter fluctuations on scales of 8 megaparsecs, a parameter called S8, which was measured differently by different techniques in ways that were difficult to reconcile within the standard model. Observations of the large-scale structure of the universe through weak gravitational lensing surveys suggested a slightly smoother distribution of matter than the cosmic microwave background measurements predicted for a Lambda Cold Dark Matter universe. Not dramatically different, a discrepancy of perhaps 2 to 3 sigma, but persistent across multiple independent surveys using different telescopes and different analysis methods. There were also tensions in the properties of the smallest galaxies. The satellite galaxy problem, the observation that the Milky Way hosts far fewer dwarf satellite galaxies than cold dark matter simulations predict, had been a long-standing concern, though its severity had been reduced by the discovery of ultra-faint dwarf galaxies that earlier surveys had missed. The too big to fail problem in which the most massive subhalos in cold dark matter simulations were denser than any of the Milky Way's known satellites could comfortably host, similarly resisted simple resolution. These small-scale challenges suggested that cold dark matter's behaviour on scales smaller than individual galaxies might not match observations, pointing either to baryonic physics effects that simulations were not capturing correctly, or to genuine modifications to the dark matter model. Webb did not resolve any of these pre-existing tensions. In several cases, it made them worse. The Hubble tension survived Webb's most precise distance ladder measurements. The galaxy abundance problem at high redshift exposed new discrepancies between Lambda Cold Dark Matter predictions and observation that existing pre-Webb tensions had not anticipated. The early quiescent galaxy problem and the overmassive black hole problem added new entries to the catalogue of observations that strain the standard framework. The cumulative weight of these tensions has prompted a serious re-examination of each component of Lambda Cold Dark Matter. The cosmological constant lambda, the dark energy term responsible for the universe's accelerating expansion, is theoretically the most uncomfortable element of the standard model. Its observed value is approximately 120 orders of magnitude smaller than quantum field theory's naive prediction for the vacuum energy density that it is supposed to represent. This discrepancy, sometimes called the worst prediction in the history of physics, has been known since the discovery of cosmic acceleration in 1998. The standard response has been to assume some unknown mechanism cancels the quantum vacuum energy almost perfectly, leaving a tiny residual cosmological constant. This mechanism has never been identified and may not be identifiable within known physics. Some researchers have proposed that lambda is not actually constant, but evolves with time, a dynamical dark energy model, which would modify the expansion history of the universe and potentially relieve some of the tensions. The cold dark matter component is similarly under scrutiny. Cold dark matter was chosen over alternatives like hot dark matter, which consists of light, fast-moving particles, because hot dark matter produces too much damping of small-scale structure. It washes out the density fluctuation that eventually become dwarf galaxies and small galaxy clusters. Cold dark matter preserves small-scale structure and produces the hierarchical formation history that observations broadly support. But the specific particle identity of cold dark matter remains unknown, despite decades of direct detection experiments, collider searches, and indirect detection efforts. The leading candidate, the weakly interacting massive particle or WIMP, has been constrained to a degree that makes its existence in the originally predicted mass and interaction cross-section range highly unlikely. Alternative dark matter candidates, axions, sterile neutrinos, primordial black holes, ultralight dark matter, have different implications for structure formation on small scales and are actively being tested by current and forthcoming observations. Inflation, the period of exponential expansion in the first fractions of a second after the Big Bang, is the third major component of lambda cold dark matter with genuine theoretical uncertainty. Inflation solves several problems with the standard Big Bang model: the flatness problem, the horizon problem, and the monopole problem. But the specific mechanism that drove inflation remains unknown. There are hundreds of theoretically viable inflationary models that differ in their detailed predictions for the spectrum and amplitude of primordial density fluctuations. Some of these alternatives have implications for the early galaxy population that might accommodate Webb's observations more comfortably than the simplest inflationary model. If the primordial power spectrum was enhanced on the scales relevant to early galaxy formation, a feature that some alternative inflationary models produce, the dark matter halos available for the first galaxies would be more massive than standard lambda cold dark matter predicts, allowing the formation of the massive, bright early galaxies Webb observes. The pressure on lambda cold dark matter from Webb's observations is not yet at the level of a definitive falsification. The standard model remains the best tested and most precise description of the universe we have. But the accumulating tensions, when viewed collectively rather than individually, suggest that the model is incomplete in ways that go beyond minor adjustments of parameters. Something in the universe's physics is behaving differently than lambda cold dark matter assumes, and identifying what that something is represents the central challenge in observational cosmology for the coming decade. What the cosmic microwave background is not telling us. The cosmic microwave background is often described as the most perfect measurement in science. The temperature map of the CMB sky, produced by the Planck satellite and its predecessors, reproduces the predictions of lambda cold dark matter with a precision that has no parallel in any other area of observational astronomy. The acoustic peaks in the CMB power spectrum, the characteristic pattern of temperature fluctuations on different angular scales, match theoretical predictions to fractions of a percent across multiple peaks. The polarization pattern of the CMB confirms the mechanism of inflation and constrains the universe's geometry with extraordinary tightness. By almost any measure, The CMB is a triumph of observational cosmology and of the Lambda Cold Dark Matter model that describes it. But the CMB is a snapshot of the universe at one specific moment, 380,000 years after the Big Bang, when the universe first became transparent and the photons of the CMB were released. It tells us about the universe at recombination with extraordinary precision. What it cannot tell us, and this is the crucial limitation, is whether the physics that operated after recombination, during the billions of years between the CMB epoch and the present, was exactly what Lambda Cold Dark Matter assumes. The CMB constrains the initial conditions of structure formation magnificently. It cannot directly constrain the subsequent evolution of those initial conditions into the galaxies, clusters, and cosmic web we observe today. This gap is where Webb's observations become critical, and it is precisely in this gap where the discrepancies between CMB-based predictions and direct high-redshift observations are appearing. The Hubble constant derived from the CMB assumes that the physics governing the universe's expansion between recombination and today is exactly as Lambda Cold Dark Matter describes: dark energy as a constant, dark matter as a perfectly cold, non-interacting fluid, no significant additional components. If any of these assumptions are wrong, the CMB-derived Hubble constant will be biased away from the true present-day expansion rate by an amount that depends on the nature and magnitude of the departure from the assumed physics. The CMB is also silent on several aspects of early galaxy formation that Webb is now measuring directly. The amplitude of the primordial power spectrum, the parameter that determines how large the initial density fluctuations were, is constrained by the CMB at scales corresponding to galaxy clusters and larger. At smaller scales corresponding to individual galaxies and dwarf galaxies, the CMB provides weaker constraints, and the power spectrum could in principle have a different shape than the simple power law that Lambda Cold Dark Matter assumes. An enhanced power spectrum on small scales would produce more and more massive dark matter halos in the early universe, directly addressing the tension between the predicted and observed abundance of early massive galaxies. The CMB is further limited by what physicists call cosmic variance at large angular scales. The universe is a single realization of a statistical process, and on the larger scales we can observe, we have only one sample from which to measure the statistical properties of the primordial fluctuations. This means the larger scale features of the CMB are subject to irreducible uncertainty. We cannot average over many observations to reduce the noise. The CMB's anomalies at large angular scales, the unexpectedly low quadrupole and octupole moments, the alignment of these low multipoles with the ecliptic plane, the so-called axis of evil, have been known since the WMAP era and remain unexplained. Whether these anomalies represent genuine departures from the simplest inflationary predictions or are statistical flukes in a single sky realization is unknown and may be unknowable from the CMB alone. Webb's observations of the early universe are therefore not simply an extension of CMB cosmology. They probe a different epoch through different physical processes using different observational techniques. The combination of CMB precision at Z equals 1100, and Webb's direct observations at Z equals 10 to 13 brackets, an enormous epoch of cosmic history, the first billion years, that neither instrument alone can fully characterize. The tensions between CMB-based predictions and Webb observations are pointing to something happening in that bracketed epoch that is not correctly described by the standard model. The CMB does not tell us what it is because its information was imprinted at Z equals 1100 and cannot directly probe subsequent evolution. Webb is seeing the consequences without having a perfect theory to interpret them through. Closing this interpretive gap is one of the most important tasks facing theoretical cosmology in the coming decade. Gravitational lensing revealed a universe behind the universe. Einstein's general theory of relativity predicts that mass curves space-time and that this curvature deflects the paths of photons passing nearby. A sufficiently massive object, a galaxy cluster, a dense concentration of dark matter, acts as a gravitational lens, bending light from more distant background sources and producing distorted, magnified, and sometimes multiple images of those sources. This effect was first confirmed in 1919 when observations of starlight deflected by the Sun's gravity during a solar eclipse matched Einstein's predictions, producing one of the most celebrated experimental confirmations in the history of physics. A century later, gravitational lensing has become one of the most powerful tools in observational cosmology, and Webb has elevated it to a new level of capability. When a galaxy cluster acts as a gravitational lens, it creates a natural telescope in space. The cluster's mass, including the dark matter that constitutes most of it, bends and focuses light from sources behind the cluster that would otherwise be too faint or too small to observe. The magnification can be dramatic, factors of 10, 50, or even hundreds in the most favourable configurations. Distant galaxies that appear as single unresolved pixels in direct imaging are stretched into arcs and rings by the lensing geometry, allowing their internal structure to be examined at resolutions that no direct observation could achieve. The cosmic frontier is made more accessible by the gravitational lens that sits in front of it. Webb has used galaxy clusters as gravitational telescopes with extraordinary effectiveness. The early release observations included images of the cluster SMACS 0723, which provided a showcase of this capability. Behind the cluster, which lies approximately 4.6 billion light-years from Earth, Webb's infrared sensitivity and resolution revealed thousands of background galaxies at a range of redshifts, many magnified by factors of several and some stretched into visible arcs that extended across significant fractions of the field of view. The lensing geometry encoded the mass distribution of the cluster itself, allowing dark matter maps to be constructed with precision that previous instruments could not achieve. The Cosmic Evolution Survey clusters, the Hubble Frontier Fields clusters observed by both Hubble and Webb, and dedicated Webb lensing programs have collectively produced a data set of gravitationally lensed high-redshift galaxies that is transforming the study of the early universe. The highest confidence extreme redshift galaxies in Webb's catalogue, including several objects at Z greater than 12, were detected precisely because they were magnified by foreground lenses. Without that magnification, they would have fallen below Webb's detection threshold, even with its extraordinary sensitivity. The lensing analysis itself has produced surprises beyond the distant galaxies it reveals. The mass distributions of galaxy clusters inferred from lensing models are more complex and more concentrated than some dark matter simulations predict. The central regions of clusters show density profiles that are steeper than the standard NFW profile, the Navarro-Frank-White profile that cold dark matter simulations produce, in ways that have been debated for years in the context of lower resolution observations and are now being examined with Webb's superior data. Some cluster cores show evidence for multiple concentrations of dark matter, suggesting ongoing mergers and dynamical interactions that are more frequent or more extreme than simulation-based cluster assembly models predict. Webb's lensing observations have also revealed objects in the distant universe that would be invisible without magnification. Not merely faint galaxies, but qualitatively new categories of objects that only the lensing amplification makes accessible. Individual giant stars at cosmological distances have been detected through Webb lensing observations, their light temporarily amplified to detectability when they happen to cross a caustic, a region of maximum magnification in the lensing geometry, in the source plane. These stellar transients are detected as brief brightenings in a lensed arc and can be used to probe the stellar populations of early galaxies at the level of individual stars, a resolution that even the largest planned future telescopes could not achieve without lensing assistance. The universe behind the universe, the population of sources made visible only through gravitational magnification, is a richer and more complex population than was anticipated. The lensed galaxy sample reveals early universe objects spanning a wider range of morphologies, star formation rates, chemical compositions, and structural properties than the unlensed high-redshift sample, reflecting the fact that lensing preferentially magnifies compact, high-surface brightness objects that are not representative of the full early galaxy population. Understanding the selection effects introduced by gravitational lensing is essential for correctly interpreting what the lens sample tells us about the early universe. The expansion rate controversy could mean new physics. The Hubble tension is described in an earlier chapter as a discrepancy between the early universe and late universe measurements of the expansion rate. It deserves a deeper examination here because the implications of the tension not resolving under Webb scrutiny have only become more significant as time has passed and additional data has accumulated. A discrepancy that persists through the most careful and precise independent measurements achievable is not a systematic error waiting to be found. It is a signal. The question is what it is a signal of. The expansion rate of the universe is determined by its content. In Lambda Cold Dark Matter, the universe contains ordinary matter, cold dark matter, radiation, and dark energy as a cosmological constant. Each component contributes to the expansion in a specific way that depends on its equation of state, the relationship between its energy density and its pressure. Matter and radiation slow the expansion through their gravitational attraction. Dark energy accelerates it through its negative pressure. The balance of these contributions at any given time determines how fast the universe is expanding. If the Hubble tension is real and Webb's confirmation of the distance ladder value makes it increasingly hard to dismiss, then one or more of these contributions must be different from what Lambda Cold Dark Matter assumes. The most actively explored possibilities can be grouped into two categories: new physics in the early universe and new physics in the late universe. New physics in the early universe would modify the acoustic peaks of the CMB, shifting the inferred Hubble constant from the Planck-derived value. The most widely discussed mechanism is early dark energy, a component of dark energy that was more significant in the early universe than it is today. If dark energy had a higher density in the few million years before recombination, it would have altered the sound horizon, the characteristic scale of the acoustic oscillations imprinted in the CMB, in a way that would shift the Planck-inferred Hubble constant upward, reducing the tension with the distance ladder value. Early dark energy models have been constructed and tested against both CMB data and large-scale structure observations. They can reduce the Hubble tension, but introduce new tensions in other observables. They do not provide a clean, cost-free resolution. New physics in the late universe would modify the expansion history between recombination and today without altering the CMB. Dynamical dark energy, a dark energy component whose density evolves with time rather than remaining constant, is the simplest such modification. If dark energy was weaker in the past than today, the expansion rate at intermediate redshifts would have been slower, and the late universe Hubble constant would be higher than the CMB prediction derived under the assumption of constant dark energy. Recent data from the Dark Energy Spectroscopic Instrument Survey, released in 2024, provided hints that dark energy may indeed not be constant, that it has weakened or strengthened at a statistically suggestive level over cosmic time. These hints are not yet definitive, but they are consistent with the direction needed to address the Hubble tension from the late universe side. Other new physics possibilities include modifications to general relativity on cosmological scales. The theory of gravity might behave differently at the largest observable scales than it does locally, producing a different expansion history. There is also the possibility of a non-zero neutrino mass in the upper range of current constraints, which would affect both the CMB and the growth of large-scale structure in ways that might shift the inferred cosmological parameters. Interacting dark energy models, in which dark energy exchanges energy with dark matter, have also been explored as potential resolutions to the tension. None of these modifications has achieved the status of a consensus solution. Each reduces the tension while introducing new complications elsewhere in the standard model. What is clear is that the universe is not behaving exactly as Lambda Cold Dark Matter assumes, and that the nature of the discrepancy is in some component of the model that affects the expansion history, either the dark energy, the dark matter, or possibly the early universe physics that set the initial conditions. Webb's confirmation that the distance ladder is not the source of error has transformed the Hubble tension from a measurement problem into a physics problem. The resolution, when it comes, will require identifying new physics. That is not a minor revision. That is a discovery. What lies beyond the observable edge? The observable universe has a boundary, but the universe itself does not. Beyond the cosmic horizon, the surface from which light has had time to reach us, space continues. The Big Bang happened everywhere simultaneously in the sense that the initial conditions that produced the observable universe also produced the space beyond the horizon. Matter, dark energy, and the same laws of physics that govern our observable patch of cosmos extend into the unobservable regions as far as we have any theoretical reason to suppose. How far that extension goes is by definition unknown and perhaps unknowable. The simplest assumption is that the universe beyond the horizon is more of the same density of matter, the same dark energy, the same distribution of galaxies and structures, essentially an infinite repetition of the pattern we observe. This is the assumption built into Lambda Cold Dark Matter, which describes the universe as statistically homogeneous and isotropic on large scales. Within the observable universe, this homogeneity is well confirmed. The universe looks the same in all directions on scales larger than a few hundred megaparsecs. Extrapolating this homogeneity beyond the horizon is reasonable, but not verifiable. More exotic possibilities are seriously discussed in theoretical cosmology. The inflationary paradigm, the mechanism that produced the observable universe's initial conditions, generically predicts that inflation continues indefinitely in regions outside our horizon, constantly nucleating new observable universes with potentially different physical parameters. This is the multiverse, a concept that remains controversial because it makes predictions that are difficult or impossible to test observationally. Different bubble universes in an eternally inflating multiverse might have different values of the cosmological constant, different particle masses, different coupling constants. Some versions of string theory predict a landscape of possible vacuum states, each with different physical laws, of which our observable universe occupies one. These ideas are mathematically developed and theoretically motivated, but they remain at the boundary between physics and philosophy, because no current observational program can test them. What Webb's observations tell us about what lies beyond the horizon is indirect but not trivial. The edge effects of large-scale structures, if the cosmos contains structures larger than the observable universe. Their gravitational influence might produce subtle anisotropies in the CMB or in the distribution of distant galaxies on the largest observable scales. The large-angle anomalies in the CMB, the unexpectedly low quadrupole, and the alignment of low multipole moments could, in some interpretations, reflect the influence of structures beyond the horizon. These interpretations are speculative, and the anomalies are consistent with statistical fluctuations in a standard Lambda Cold Dark Matter universe. But they represent the kind of observational hint that motivates theoretical exploration. Webb also probes the very early universe in ways that constrain inflationary models, which in turn constrain what the universe beyond the horizon might look like. The spectral index of the primordial power spectrum, the way the amplitude of density fluctuations varies with scale, is a key inflationary observable. Different inflationary models predict different spectral indices, and the Planck measurements constrain this parameter tightly. Webb's observations of early galaxy clustering and the matter power spectrum on small scales provide complementary constraints that favour or disfavour different classes of inflationary models. The inflationary model that best fits the data determines, in a theoretical sense, the likely character of the universe beyond the horizon. The honest answer to the question of what lies beyond the observable edge is that we do not know, and that the tools available to us may never be sufficient to determine it with certainty. The cosmic horizon is a fundamental observational limit imposed by the laws of physics. No telescope, however large or sensitive, can see beyond it, because the light from beyond has not had time to arrive. The universe beyond our horizon is hidden not by dust or distance in the ordinary sense, but by the finite age of the cosmos and the finite speed of light, barriers that no technological advance can overcome. Webb has pushed the observable frontier closer to that limit than ever before, and what it has found in that frontier has been surprising. What lies beyond remains the deepest unknown in all of science. The universe may be far older than we thought. The age of the universe is not a controversial number in mainstream cosmology. The Standard Model, calibrated against the cosmic microwave background, the distance ladder, the abundances of light elements produced in Big Bang nucleosynthesis, and the ages of the oldest stars, converges on approximately 13.8 billion years with an uncertainty of less than 1%. This is one of the most precisely determined numbers in cosmology, and the consistency of the age derived from independent methods is itself a powerful confirmation of the Lambda Cold Dark Matter framework. But consistency between methods that all assume the same underlying model is not the same as model-independent truth. If Lambda Cold Dark Matter is wrong in some of its fundamental assumptions, the age derived from CMB parameters calibrated within that model could be wrong as well. The Hubble tension itself is an example of this. The CMB-derived Hubble constant and the distance ladder. Hubble constant differ, and the age of the universe inferred from each is different. A higher Hubble constant means a faster expanding universe means a younger universe. A universe that has been expanding for less time than the Planck preferred value implies. If the true Hubble constant is closer to 73 kilometers per second per megaparsec than to 67, the universe is somewhat younger than 13.8 billion years. If it is higher still, the implied age drops further. But the most dramatic age challenge comes not from the Hubble tension, but from the oldest stars. The age of a star can be estimated from stellar evolution theory. The properties of a star's surface temperature, luminosity, and chemical composition constrain its evolutionary state and hence its age. Globular clusters, which are dense assemblages of stars that form together from the same gas cloud, contain some of the oldest stars in the Milky Way. If the universe is 13.8 billion years old, no star can be older than 13.8 billion years. They have to have formed after the Big Bang. Historically, estimates of the ages of the oldest globular cluster stars have occasionally approached or exceeded the standard cosmological age, creating tension that has been resolved as stellar age estimates have been refined. The oldest globular cluster stars currently estimated to be among the oldest known objects are in the range of 13 to 14 billion years. These estimates carry uncertainties of roughly 500 million to 1 billion years in each direction. so they are consistent with a 13.8 billion-year-old universe. But some analyses of specific extremely metal-poor stars, stars with chemical compositions consistent with having formed from the nearly pristine gas of the very early universe, have yielded age estimates at the upper end of, or slightly exceeding, the standard cosmological age. These extreme cases are individually uncertain and should not be taken as definitive evidence, but they raise the question of whether the universe might be somewhat older than 13.8 billion years. A cosmological model with a slightly different content or expansion history could accommodate a somewhat older universe while maintaining consistency with CMB observations. If dark energy is slightly stronger in the past than the cosmological constant model assumes, a modification that is in the right direction to address the Hubble tension from one angle, the universe's expansion would have been slightly slower in the past, implying a somewhat older age for a given observed expansion rate today. Some alternative cosmological models constructed to address the Hubble tension produce universe ages closer to 14 or 15 billion years. Webb's role in the age question is indirect but significant. The telescope's observations of the oldest and most metal-poor stars in nearby galaxies and globular clusters, using its infrared sensitivity to resolve individual stars in crowded stellar populations, provide improved age estimates that constrain the maximum permitted age of the universe. If Webb were to identify stars with reliable age estimates significantly exceeding 14 billion years, it would provide direct evidence that the universe is older than Lambda Cold Dark Matter currently allows, constituting a serious falsification of the Standard Model's age prediction. Conversely, if the most refined stellar age estimates consistently fall below 13.5 billion years, it would reinforce Lambda Cold Dark Matter's age prediction and constrain alternative models. The age of the universe is a fundamental observable that anchors the entire history of the cosmos. If it is wrong, even by a billion years in either direction, the timeline of galaxy formation, black hole growth, chemical enrichment, and structure assembly is affected throughout. A universe that is older than we think had more time to produce the massive early galaxies Webb finds. An older universe would be more consistent with the existence of quiescent galaxies at z equals 6, because their star formation would have had more time to run its course before reaching the observed epoch. The age question and the early galaxy problem are connected, and resolving one may illuminate the other. The one finding that threatens the entire Standard Model. Across the preceding chapters, a pattern has emerged from Webb's observations that goes beyond any individual discovery. It is not merely that early galaxies are too massive, or that the Hubble constant is discrepant, or that quiescent galaxies appeared too early, or that black holes were overmassive, or that reionization was patchier than expected. Any one of these findings taken alone could be absorbed into existing theory with appropriate modifications. Theorists are skilled at adjusting parameters, invoking new feedback mechanisms, or citing observational uncertainties when a single data point misbehaves. Science accommodates outliers. What it cannot easily accommodate is a systematic pattern of outliers, all pointing in the same direction. The disturbing finding is the pattern itself, the consistent, systematic direction of the discrepancies. The early universe, as Webb sees it, is repeatedly more evolved, more organized, more chemically complex, more massive, and more active than the Standard Model predicts it should be. The deviations are not random. They point in the same direction, and that direction is toward a universe that assembled its first structures faster, more efficiently, and more dramatically than Lambda Cold Dark Matter allows. This systematic deviation is what distinguishes Webb's findings from the routine refinement of astrophysical models that characterizes normal scientific progress. When a theory is essentially correct and observations deviate randomly from its predictions, some deviations are high and some low, and the average matches the theory. When a theory is missing something important and observations systematically deviate in one direction, it means the missing element was contributing in that direction all along, suppressing or enhancing some physical process in a way that the standard model did not account for. The history of physics is full of moments where this kind of systematic mismatch preceded a fundamental revision. The precession of Mercury's orbit deviated from Newtonian predictions in a single, consistent direction for decades before general relativity explained why. Webb's systematic deviations carry that same character, not noise, not scatter, but a signal with a direction. The physical process most likely to be systematically underestimated in the early universe is the efficiency of structure formation itself, the rate at which dark matter halos grow, the rate at which gas cools and forms stars within those halos, and the rate at which those structures merge and build larger assemblages. Anything that accelerates these processes beyond what Lambda Cold Dark Matter predicts would produce exactly the pattern Webb is observing. More massive halos forming earlier would host more massive galaxies. Faster cooling would produce higher star formation rates. More efficient feedback-free early star formation would produce higher observed luminosities. Faster black hole growth within overmassive host halos would produce the observed ratio of black hole mass to stellar mass. The entire collection of Webb's early universe surprises could, in principle, be traced to a single modification: an enhanced rate of structure formation in the first billion years. What physical mechanism could produce this enhancement? Several candidates are being actively investigated. Modified dark matter models, in which dark matter is not perfectly cold, but has a small initial velocity dispersion, or in which it interacts weakly with itself or with ordinary matter, can produce different halo formation rates than standard cold dark matter. Primordial black holes, which could have formed in the early universe before the first stars, could seed earlier and more massive structure formation by providing additional gravitational nuclei. A modification to the primordial power spectrum, specifically an enhancement of power on small scales relative to the simple power law that inflation predicts, would produce more and more massive halos in the early universe, directly addressing the galaxy abundance problem. Each of these candidates has a different theoretical motivation and a different set of observational consequences, meaning that future Webb data and complementary surveys could, in principle, distinguish between them. The next few years of Webb observations, combined with data from the Euclid Space Telescope and the Vera Rubin Observatory, will be decisive in testing which modifications survive contact with a larger and more complete dataset. Enhanced power on small scales is particularly interesting because it would connect Webb's galaxy formation discrepancies to the small-scale tensions in the dark matter model that predate Webb. If the primordial power spectrum has a feature, a running of the spectral index, a bump, or a break, that boosts power on galaxy and sub-galaxy scales, it would simultaneously produce more early galaxies, alter the abundance of dwarf satellites in a way that might address the satellite problem and affect the internal structure of small galaxies in ways that relate to the core cusp tension. A single modification to the early universe's initial conditions could potentially address multiple tensions simultaneously. That kind of theoretical economy, one change fixing several problems at once, is exactly the kind of signal that physicists learn to take seriously. The most conservative interpretation of Webb's findings is that the Standard Model is correct in its broad strokes, but requires improved modelling of the baryonic physics. Star formation, feedback, chemical enrichment that operates within the dark matter framework Lambda Cold Dark Matter correctly describes. Better simulations with higher resolution and more realistic physics might reproduce Webb's observations without modifying the cosmological model itself. This interpretation is scientifically respectable and is pursued vigorously by a large community of computational astrophysicists. The challenge is that the required improvements in baryonic physics need to consistently push star formation efficiency higher, feedback efficiency lower, and chemical enrichment faster at high redshift, in ways that appear to require a coordinated set of changes rather than a single correction to an identified error. When fixing a theory requires adjusting multiple independent components simultaneously in the same direction, it begins to resemble not a refinement, but a rescue operation. The more radical interpretation is that the standard cosmological model is missing an ingredient that significantly affects structure formation in the early universe. This ingredient could be a modification to dark matter, a non-constant dark energy, a different inflationary spectrum, or something not yet theorized. This interpretation is not currently supported by a specific, well-developed alternative model that explains all of Webb's observations simultaneously. It is supported by the systematic nature of the discrepancies and the difficulty of accommodating them within Lambda Cold Dark Matter using known physics. What Webb's most disturbing finding actually means, in the broadest sense, is this: the universe's first chapter was not what we wrote. The script we assembled over 30 years of precision cosmology described an early universe that was primitive, chaotic, and slowly building its first structures from simple ingredients under the patient influence of gravity. Webb found instead an early universe that was already organized, already building massive and complex structures, already hosting chemical enrichment processes and dead galaxies and oversized black holes, on a timeline that our best theories do not accommodate without modification. The universe did not wait for us to finish theorizing about it before showing us what it was actually doing. It presented the evidence in the form of ancient photons traveling for nearly 14 billion years and left us to update the theory to match. That is not a crisis. That is science working exactly as it should. And the answer, when it arrives, will almost certainly be stranger and more illuminating than the model it replaces. Observational tensions in early universe cosmology. The James Webb Space Telescope was not built to break cosmology. It was built to extend it, to push the frontier of the observable universe further back in time and fill in the details of a picture that decades of observation had sketched in broad outline. What it found instead was that the sketch was wrong in ways that matter. The earliest observable galaxies were too large, too organized, too chemically sophisticated, and in some cases already too dead for the timeline that standard theory provided. The expansion rate of the universe defied reconciliation. The first black holes were already too massive. The reionization of the cosmic hydrogen was more chaotic and more extended than anyone had mapped. Taken together, these findings do not merely refine our picture of the early universe. they redraw it. This is what science looks like when it works at its highest level. Not the confirmation of what was expected, but the confrontation with what was not. The discomfort of a well-tested model encountering observations it cannot cleanly accommodate is not a failure of the model's builders. It is the signal that nature has more to say than the model captured. Every revolution in physics began with exactly this kind of productive discomfort. Measurements that did not fit, predictions that missed, patterns that pointed beyond the current framework towards something new. The standard cosmological model will either be refined to accommodate what Webb has found, or it will be replaced by something that can. Either way, the universe will be better understood. What Webb has given us, beyond the specific discoveries and the specific tensions, is the closest look humanity has ever taken at the beginning of everything. The photons it collects from the edge of the observable universe are the oldest light we will ever see, ancient messengers carrying information about a cosmos barely emerged from the formless fire of the Big Bang, already building the structures that would eventually become galaxies and stars and worlds, and the minds that wonder about them. Whatever those photons are telling us that we have not yet learned to hear, the act of receiving them and taking them seriously is among the most extraordinary things our species has ever done. The edge of the universe looked back at us, and what it revealed was not confirmation of what we thought we knew. It was an invitation to know more.